The James Webb Telescope, or JWST, has been one of the most ambitious projects undertaken by NASA. The telescope promises to uncover previously unknown and hidden secrets of the universe that its predecessors were unable to see. One of these secrets is the terrifying discovery of the warp bubble. What is the warp bubble? How will it change things? Stick around to find out as we talk about the James Webb Telescope and the discovery of the warp bubble. First, the James Webb Space Telescope. The James Webb Space Telescope is the most advanced and complex space observatory ever made. The project has been under construction for a long time, and its launch was highly anticipated. Finally launched on Christmas Day, it is NASA's most powerful telescope ever, surpassing its predecessor, the Hubble Space Telescope. Once the JWST was launched, it will undergo a series of science and calibration tests, including the deployment of the sun shield, as well as the telescope deployment, instrument turn-on, and telescope alignment. According to the Space Telescope Science Institute, the best images from JWST will start to appear about 6 months after launch, though we may possibly get to see some first light images slightly earlier. It took 30 days for the James Webb Space Telescope to travel nearly 1 million miles to its permanent home, a Lagrange point, a gravitational stable location in space. The telescope got to L2, the second Sun-Earth Lagrange point, of the 24th of January 2022. L2 is a spot in space near Earth that lies directly opposite to the Sun. This orbit will help the telescope to stay in line with the Earth as it orbits the Sun. L2 has been a pretty popular spot for other telescopes like the Herschel Space Telescope and Planck Space Observatory. The James Webb Space Telescope came into being as a result of an impressive international collaboration between NASA, the European Space Agency, ESA, and the Canadian Space Agency. According to NASA, this project involved over 300 universities, organizations, and companies across 29 US states and 14 countries. The expected duration for the James Webb Space Telescope is 5 years, but according to the ESA, the goal is 10 years. The biggest goal of this giant project is to uncover secrets about the origins of the universe, the formation of planets, galaxies, and the like. Using infrared sensors, that JWST will be able to capture infrared light being given off by faraway planets. Not just the light from faraway planets, though, it will also be able to sense infrared light from some of the earliest stars and galaxies in the universe, allowing us to take a look at our past and discover our origins. The telescope will work in collaboration for the first few years with the Hubble Space Telescope, which still remains in good health. What is a warp bubble? Before we talk about what it would mean for space travel if we were to discover a warp bubble, we first need to define what a warp bubble actually is. Now, to be able to fully understand what a warp bubble truly is, we need to have a deep understanding of some very complicated mathematical concepts. But we're gonna make do with a very basic definition. A warp bubble is a region or bubble in space that is contracted at the first and expanding at the back. This allows the contents inside the bubble to travel at speeds faster than light without violating any known laws of physics. Why does it not violate any physical laws, you might ask? Well, that's because the contents inside the bubble are actually traveling at light speed. But imagine it being like surfing a region of condensed space. So technically, you're not faster than the speed of light, and therefore no physical laws are broken. But why would traveling at light speed be a problem? And how would warp bubbles be able to bypass that problem? Well, to explain that, we need to take a look at one of the most widely known theories by the famous scientist Albert Einstein. Einstein published the theory of special relativity and general relativity in 1905 and 1915. These two theories were the hallmark of Einstein's life as a theoretical physicist and would forever change the landscape of the world of physics. In his theory, Einstein talks about the concept of time dilation and what it would mean if an object were to travel at the speed of light. According to Einstein's theory, if an object approached or traveled at the speed of light, the passage of time would change in relation to the observer. This means that the object would cover insanely large distances pretty quickly. But everything that's not traveling at the same speed covers that same distance in a much longer time frame, meaning that things not traveling at the speed of light will go through a lot of changes during that time. To break this down with an easy example is to think of a space traveler traveling at light speed. The traveler will get to their destination in a relatively relatively short span of time. But for everyone else, time moves slower. So while the traveler might not be experiencing any changes to themselves, everyone and everything they probably knew would die or drastically change in that same time frame. That sounds pretty terrifying. But the neat thing with a warp bubble is that it easily overcomes the time dilation problem. How so? The key difference here is that for time dilation, the object travels at light speed through space. But in a warp bubble, space-time itself is moving. So the object can surpass the speed of light while staying within the bounds of physical laws. Because of this, the space around the warp bubble remains unaffected, meaning that an hour of traveling inside a warp bubble equates to exactly an hour passed in real time. Pretty cool, right? Next, implications of the warp drive on space travel. Warp bubbles sound pretty fascinating. To actually consider what the discovery of a warp bubble might mean for the future of space travel, we need to talk about Miguel Alcubierre. Alcubierre is a Mexican theoretical physicist who has spent a lot of time theorizing about warp bubbles. In a paper he published in 1994, he posited that a warp bubble would allow one to cover arbitrarily long distances in arbitrarily short times, without locally breaking the speed of light. To explain what he meant, he gave the example of Proxima Centauri. Proxima Centauri is the closest star to Earth. At a distance of approximately 4.25 light-years away, that's pretty far. But according to Alcubierre's calculations, traveling in a warp bubble would theoretically allow you to go all the way to Proxima Centauri in only about a month, based on the time measured using the clocks of the spacecraft and of mission control. In a 2017 lecture, Alcubierre explains the phenomenon of comparing it to the experience of being on a moving walkway airport. By imagining that the floor behind you is being created out of nothing, and in front of you it's being destroyed, moving you along. In theory, a warp bubble could move you along this walkway and ride the bunching space-time fabric in such a way that its relative time remained slow, while simultaneously moving great distances faster than the speed of light. But the Alcubierre drive faces a roadblock. It's because the warp bubble would need to be driven using negative energy. Now, creating negative energy is no joke, especially for a project this big. To create enough negative energy for driving a warp drive, you would need to use a huge amount of mass in order to create an imbalance between particles and antiparticles. For example, say an electron and an anti-electron appeared near the warp drive. One of them would end up getting trapped by the mass, resulting in an imbalance. This imbalance would create negative energy density. This negative energy is then used by Alcubierre's warp drive to create a warp bubble. But to generate enough negative energy, you would need a lot of matter. Alcubierre's estimations predict that for a warp drive with a bubble of 100 meters, you would need the mass of the entire known universe, which sounds pretty much impossible. In 1999, Chris van der Broek showed that by expanding the volume inside the bubble while keeping the surface area constant would significantly bring down the massive energy requirements to just about the mass of the sun, but that is still a big ask and sounds pretty hard to be able to do, even with modern technology. But all hope is not lost for the dream of warp bubbles and warp drives. Even though the negative energy requirements might make it sound like a fever dream, but newly published research by theoretical physicist Eric Lentz suggests that we might not need to use so much energy. In fact, we may be able to do away with the negative energy requirement altogether. Lentz went over Alcubierre's research that led him to arrive at the massive negative energy requirements. Lentz found that Alcubierre had only considered comparatively simple linear relationships of his warp bubble. Lentz got around this problem by opting for more complex hyperbolic equations. This led Lentz to come up with an entirely new warp bubble than his predecessors. But of course, Lentz's warp bubble also requires huge amounts of energy, the plus side being, however, that Lentz's bubble only needs positive energy according to his calculations. Warp bubbles definitely are something that we all wish existed, but until science can come up with a way to meet the huge energy demand, we'll continue to remain in the realm of science fiction. But the upside is that we're definitely closer to figuring them out now than we've ever been before. That's a wrap for this video. See you in the next one.